is called concavity and points of inflection. Okay, so what we're going to start with here is talking about things that are concave, concave up and concave down. And you've probably heard that word concave before, especially if you've taken physics, or I think even in science 9 or 10 or something, you talk about lenses and stuff. And what you hopefully remember is that a concave lens looks like this, right? This surface right here, as the light rays come here, this is the concave surface right there. The other side would be convex if it bends away from you, but if it's bending in like this, it's called concave. So this function right here, would you say it's concave up or down? Hopefully you can see that if this was a lens, the concave lens would be like this, that's up. So this is concave up, and this one here is concave down. Now what I want to do here is draw some tangent lines to some of the points on this function right here. So at this point, for example, the tangent line would look like this. Here it would look something like this. Here it would look something like this. Okay? And for this one, if we were to draw tangent lines, like at this point, it would look like this. This one, it would look like, whoops, this. This one, it would look like that. Like that. Now, what's the difference between all these tangent lines and all those tangent lines? The difference is that all these tangent lines are below the function. All these tangent lines are above the function. So if something's concave up, like this one, this graph right here is concave up, then the curve lies above all its tangents on the interval of interest. And if it's concave down, the curve lies below all its tangents on the interval of interest. Okay. There's also something called a point of inflection, which we'll be talking about a lot today. This is where a curve changes from concave upward to concave downward, or vice versa. It could go from concave down to concave up. So what that might look like, for example, is a curve that looks like this. Okay? Now, if there's a point right around here, which is our point of inflection, and the reason that this is the point of inflection is because if you look down in this region, is this concave up or concave down? This is concave up. If you're not clear about that, draw your tangent lines and you'll see all the tangent lines here are below. But once you get up here, this is concave down because all the tangent lines up here are like this. So I don't know if you want to put all those tangent lines, it might make it too messy. If you wanted to, you could put concave up and concave down. Stepping back, a little review here for this one question. What does it mean for the first derivative to be positive? So if you think back when we first started talking about derivatives, what do we say derivatives are always referring to? They're referring to the slope of the tangent line. So if the first derivative is positive, then the tangent lines must have positive slopes. Okay, that's good. We've also seen in the last bunch of classes that when you find the first derivative is positive, it means that the function is increasing. So that's review. This is what we already knew. Now, this is new. What does it mean for the second derivative to be positive? Well, when you look at the second derivative, you're looking at the rate of change of the slopes of the tangent lines. So in other words, if you have a positive second derivative, it means that the slope of the tangent lines are getting bigger and bigger and bigger and bigger. The slope of the tangent lines are increasing from left to right. Now, if the slope of the tangent lines are increasing as you go left to right, do you see that's exactly this situation here? I have three tangent lines here, and as I draw the first one here, and then I draw the next one, oh, that one's steeper, and I draw the next one, oh, that one's steeper still. If I was drawing another one here, it'd be even steeper still. So as I'm going from left to right here, the slopes of the tangent lines are getting steeper and steeper and steeper. So that means it will be concave upward. We can use the second derivative to figure out whether the graph is concave upward or concave downward. Now, of course, we could do the exact same, these two questions again, and say what if the first derivative is less than 0 and what if the second derivative is less than 0. I didn't bother doing that just for space, but I'll quickly run through it here. It would mean the function's decreasing, it would mean the tangent lines have negative slopes, and it would mean that the slope of the tangent lines is decreasing. Right? The second derivative, if it's less than 0, that would mean the slope of the tangent lines is getting less and less and less. And that is this situation up here. Right? If I look at this point, I have a pretty steep slope, and then I look at this one, oh, it's not as steep. I look at this one, it's getting less steep. I look over here, it's even less steep. They're getting less and less and less as we move from left to right. So if that's the case, you end up with concave down, just like this one is here. So this allows us to have a test for concavity to see whether something's concave up or concave down. If f double prime of x, in other words, if the second derivative is positive, if it's greater than 0 for all x in an interval that we'll call I, then the graph of f is concave upward on that interval. And if the second derivative is less than 0, it's negative for all x in that interval, then the graph of f is concave downward. How do I make such a stupid mistake? Downward on I. And there's actually one more point. There will be a point of inflection at any point where the second derivative changes sign. So any point where the second derivative goes from negative to positive, there's going to be a point of inflection. Any point where the second derivative goes from positive to negative, there's going to be a point of inflection. Let's try one out. Consider f of x equals x to the fourth minus 8x cubed. Find the intervals of increase and decrease, which is what we did last time. Find the local maximum and minimum values, which is what we've done in the previous days too. Find intervals of concavity, that's what we're going to do right now. That's what we learned right now. Find points of inflection, we just learned that now, and sketch the curve. This is getting to be a lot of work, isn't it? That's why the questions in this chapter are absolutely crazy, because it just gets loaded more and more stuff into a single question. Okay, we've got to get the intervals of increase. How do we do that? We're going to start by taking the first derivative. So f prime of x equals 4x cubed minus 3 comes down, multiplies the 8, you get 24x squared. And now what we need to do is we need to get the critical values, or critical numbers, or critical points, whichever one you want to call it. Critical numbers. So in order to get the critical numbers, we ask ourselves, what would make the derivative not exist? Well, it always exists. There's no denominator here, there's no square roots or anything, so it always exists. So the other thing we want to know is, what would make the derivative, 4x cubed minus 24x squared, what would make it equal 0? Okay, let's factor out 4x squared, and you're left with x minus 6 equals 0. So here's your two factors, 4x squared and x minus 6. What would make 4x squared equal 0? If x is 0. What would make x minus 6 equal 0? If x is 6. So these are our critical numbers. We're going to put these numbers on the wiggle graph. And we're going to test those intervals right here. And we want to know whether it's going to be positive or negative. So let's do that. Let's try a number up here. I'll try 10. 10 squared, well, first of all, this is squared. You don't even really need to worry about this. Whether you put a positive or negative in here, it's going to be positive. I really only care about this bit here. So 10 minus 6 is 4. This is positive, which means it's increasing here. Between 0 and 6, how about 3? 3 minus 6 is negative 3. Remember, this is going to be positive because you're squaring it. 3 minus 6 is negative 3, so it's negative. It's decreasing. Something less than 0. How about negative 2? Negative 2 take away 6, that's still negative. So we have another region here where it's decreasing. So they want us to write the intervals of increase and decrease. Let's do that like this. We're going to say increasing is from 6, but not including 6, right? 0 and 6 is where it's not increasing nor decreasing. So we're going to say from 6 all the way up to infinity. And for decreasing, a common mistake people say here is from negative infinity up to 6, but it's not exactly true. I mean, it's not bad at all that you said that, but it's actually from negative infinity up to 0, and also from 0 up to 6, but none of that is inclusive. So you can't just say from negative infinity to 6, because that would include 0, and this doesn't include 0. At 0, it's neither increasing nor decreasing. Okay, so we found the intervals of increase and decrease. Now we have to find local maximum and minimum values. So I'm going to write max and minimum. To find those, you look to see where do we go from increase to decrease or decrease to increase. So we have that right here. We go from decrease to increase. If something goes decrease to increase, we have a minimum right there. So our minimum is at 6, comma, what if we want to know which point it is? Well, you'd plug 6 into where? you'd plug it into the function up here. So you'd find, I don't know, I guess I'll just write this out here. It's going to be a lot of writing in this question. F of 6 equals 6 to the 4th minus 8 6 cubed. 6 to the 4th is 1,296 minus 8 times 6 cubed is 216. So you get 1,296 minus 1,728, and if you subtract that, you end up with negative 432. So our minimum value, it's going to be interesting to graph this, is at 6 comma negative 432. How about our maximum? Is there a local maximum? No. In order to get a local maximum, you'd have to have two intervals side by side that are increase and then decrease, and we don't have that. So there is no maximum value. All right, this is part of the information we need. The rest we need to do is we need to get the intervals of concavity and the points of inflection. That's what we learned today. So how are we going to do that? We're going to take the second derivative. I'll change colors here. So we're going to take the second derivative. Here's the first derivative right here. Take the second derivative. Well, bring the 3 down and multiply by 4, you get 12x squared. Bring the 2 down and multiply by 24, negative 24, you get negative 48x. And then really what you're going to do is the exact same thing you did up here. You have to ask yourself, when does this not exist? It always exists. When does this derivative, this second derivative, 12x squared minus 48x, when does it equal 0? Well, again, we're going to factor out, this time at 12x, we're left with x minus 4. So we end up with x equals 0 or x equals 4. So what I call these your potential inflection points. They won't necessarily for sure be inflection points, but they're potential inflection points. So I call these the pips. That's not a real math term, but potential inflection points are the 0 and the 4. Guess what you do with those? You put them on a wiggle graph. Isn't this great? You're just doing exactly the same thing. And now you're going to try these intervals. Where are you going to try these intervals in? You're going to try them right here. I mean, or here, but I like this one because it's factored. So let's do that. Up here, we'll try 10. 12 times 10, that's definitely positive. 10 minus 4, that's positive. Positive times positive is positive. Now, what's that mean? That doesn't mean that this is increasing here. Remember, we're talking about concavity here. And what we learned, right down here, we found that if the second derivative is positive, like this one is, then the graph is concave up. So we know that in this interval from 4 onwards, that it's going to be concave up. What I usually put for that is just CU, concave up. Put concave up if you can't remember that, but I'm going to put CU. Okay, let's pick a number between 0 and 4. How about 2? 12 times 2, positive. 2 minus 4, negative. Positive times negative is negative. So this interval between 0 and 4, the graph is concave down. Number less than 0. How about negative 10? 12 times negative 10, definitely negative. Negative 10 take away 4, definitely negative. Negative times negative, positive. The graph is going to be concave up in this region. So we got to write down our regions of concave up and concave down. I'll do that in purple again over here. Concave up. It's concave up from negative infinity up to 0, as well as from 4 up to infinity. And it's concave down from 0 to 4, non-inclusive. Okay, it's time to look for inflection points. Inflection points is where the signs change in the second derivative. So you're going to have a couple inflection points here. Inflection points. I don't know where I'm actually going to draw the graph. I have no room at all. Inflection points are going to be at 0 comma something and at 4 comma something. Now, how do we figure out what the y value is? Again, if you're actually looking for a point on the function, you have to go back to the original here. So you're going to have to find f of 0, which is lovely. 0 take away 0 is 0. So you know you have an inflection point at 0, 0. And the other point, you have to plug 4 into here. So that's not as easy. You're going to have 4 to the 4th power, which is 256. I don't know. Where am I going to do this? F to the f of 4 equals 4 to the 4 minus 8 times 4 cubed, which equals 256 minus 8 times 64. So that's 256 minus 512. And if you do that, you're going to get negative 256. So inflection point at 4 comma negative 256. Okay, I think we're ready to graph this. Oh, except for one thing. It'd be nice to get the x and y intercepts. Well, to get the y-intercept, you put 0 into the x. 0 minus 0 is 0. And we actually already have that point, 0, 0, so that's fine. In order to get the x-intercepts, so let's do this up here, I guess. To get the x-intercepts, what you would do is you put 0 in here, so you'd have 0 equals. Let's factor this, so you take out an x cubed, and you'd have x minus 8 left over, which means your x-intercepts would be at 0, which we already know. Again, we have that point, 0, 0. And there's also an x-intercept at 8. So that's very useful as well. We're going to use that point. Okay, so that's an important point, this x equals 8. And other important points are 6 and 0 and 4. We need to put 0, 4, 6, and 8 on this. So let's do that. 0, 1, 2, 3, 4, 5, 6, 7, 8. These are the important points to put on here. Now we know it goes through 0, 0, so I can put a point there. I know it goes through 4, negative 256. What the? Negative 256. Oh my gosh. Okay, I'm just going to put it right there, and I'm going to label this negative 256. And what other points do we have? 6. When does it go through 6? At negative 432. Of course it does. Negative 432. So somewhere around here I'm going to put negative 432 and put that dot there at 6. And at 8, where was that point? The 8. That was the x-intercept, wasn't it? Yeah, 8, 0 would be our point there. So we also need to put a point here. Okay, now we need to see whether it's increasing or decreasing in different intervals. So we have it's increasing from 6 to infinity. So from this point here at 6 to infinity, it's always increasing. Also, we can see it's always at that same interval when it's bigger than 6, it's always concave up. So what we know that's going to look like, it's going to look something like this. It's always increasing and it's always concave up. Okay, between 0 and 4, it's always concave down. And between 0 and 4, it's also always decreasing. So I can draw that. I want it to be decreasing and concave down. So it's going to go like this. And then below 0, it should be concave up and it should be decreasing. So concave up would look something like this. And if you look from left to right, that's definitely decreasing. It's not the greatest there. Probably better like that. Okay, and this is a pretty good approximation of what the graph looks like. Okay, one more. This time we don't have to draw the graph and all that kind of stuff. We just have to find where it's concave up and concave down. And if that's all you're interested in, then all you need to worry about is the second derivative. So we got to get first and second derivative. We're using what? The quotient rule here. So to get the quotient rule, remember, we take the derivative of the top, which is 1, and multiply by the bottom, x squared plus 1. Then we subtract, we rewrite this top one, and we take the derivative of the bottom, which is 2x, and you divide all that by the bottom squared. Right? If you don't remember, I'll just quickly write right here. There's your quotient rule. Okay, let's simplify. That would give us x squared plus 1 minus 2x squared. And don't expand this, just keep it like that. X squared plus 1 squared. X squared minus 2x squared. Well, I'm going to put the 1 first. So I have 1 minus x squared, because 1x squared minus 2x squared is negative 1x squared. And all over x squared plus 1 squared. So that's our first derivative. We can go straight to the second derivative, because all we're looking for is whether it's concave up and down and points of inflection. Okay, we got to use the quotient rule again. So we take the derivative of the top, which is negative 2x, and multiply by the bottom, x squared plus 1 all squared. Take away the top, 1 minus x squared, times the derivative of the bottom. Derivative of the bottom, you're going to have to do the chain rule. So you have something squared. Bring the 2 down, keep the something the same, and drop that 2 down to a 1, and then multiply by the derivative of the inside. The derivative of the inside is just 2x. All that is divided by x squared plus 1 squared, but now you have to square that. Alright, we got quite a bit of simplifying to do here. Now, don't expand all this out. I can see there's an x squared plus 1 here and x squared plus 1 there. Chances are you're going to be able to factor that out. So let's just keep this first one the same. Negative 2x, x squared plus 1 all squared, minus, now we've got a 2 and a 2x, so you got 4x. Then we've got, I'm going to write this one next, the x squared plus 1. And we also have this 1 minus x squared. All over x squared plus 1 Squared, squared, you multiply those, it's now to the fourth power. So here's where you can take out a greatest common factor, where the two things you're looking at are this bit and this bit. So I see I have a negative 2x here and a negative 4x here. So I could take out a negative 2x and then have x squared plus 1 squared and x squared plus 1. So you could take out x squared plus 1. That's my greatest common factor. What do I have to multiply all that by to get this first bit here? Well, you need to multiply by another x squared plus 1. Plus, right, because it's negative 2x times what equals negative 4x times positive 2. And then we have the x squared plus 1 taken care of. So we just have this 1 minus x squared that we'd have to worry about. And that's all over x squared plus 1 to the fourth. Now all we want to do is simplify the stuff in the square bracket. So we'll have y double prime equals negative 2x. Oh look, we have x squared plus 1 and x squared plus 1 to the fourth here. So I can get rid of this and get rid of one of those, so it's now a 3. Okay, so x squared plus 1, then I'll do distributive property here, plus 2 minus 2x squared all over x squared plus 1 cubed. I think we're on our last step here. Leave this negative 2x out here. We've got 1 plus 2 is 3, and we've got 1x squared minus 2x squared, which equals negative 1x squared, and that's all over x squared plus 1 cubed. So this is our second derivative. Now what we want to do is we want to find the pips, right? We want to find where are the points that are potentially inflection points. How do you do that? You do it just like we've done the last bunch of days. You ask yourself, when does this not exist? Well, this would not exist when the denominator equals 0. But if you look at this, you're squaring something. So whether this is positive or negative, it's going to be squared and become positive. Or it could be 0 if it's 0 squared. Then you're going to add 1. So even if it was 0, it's now 1. And then you cube it. Well, positive cubed is still cubed. It's impossible for this to be negative. So the denominator is always positive. So you don't have to worry about when it doesn't exist. What you do have to worry about is when does this equal 0? Well, what would make this equal 0 is whenever the second derivative, which is negative 2x times 3 minus x squared, whenever that equals 0. So that would be the case when negative 2x equals 0, and also when 3 minus x squared equals 0. Divide both sides by negative 2 here, you get x equals 0. So that's one of your pips. Move the negative x squared over, you get 3 equals x squared. Take the square root of both sides, you get plus or minus the square root of 3. So those are 2 more pips. Actually, turns out you have 3 pips here. We got to put them all on a wiggle graph. So we're putting on here negative root 3, 0, and root 3. And what's important when you're doing stuff like this in the wiggle graph, you need to know approximately how much root 3 is. Otherwise, when you're doing your intervals, you won't know what test point to pick. So you might need to take a calculator here and figure out what root 3 is. And it turns out that it's approximately 1.73 is approximately how much root 3 is. So that'll help us when we're doing our intervals here. So let's do that. Let's try this out. We're going to plug our points into here, I would say. Remember, the bottom's always going to be positive, so you don't even really need to worry about that. You just need to worry about this stuff up here, the numerator. So let's pick a number bigger than 1.73. How about 2? So negative 2 times 2 is negative 4. It's negative. 2 squared is 4, and 3 take away 4 is negative 1. That's negative. So negative times negative is positive. Up here it's positive. What's that mean? That means it's concave up here, because we're doing second derivative. It's telling us whether it's concave up or concave down. Okay, something between 0 and 1.73. How about 1? Negative 2 times 1? Negative 2, so it's negative. 1 squared is 1. 3 minus 1 is 2. It's positive. Negative and positive is negative. It's concave down. Okay, between 0 and negative 1.73. How about negative 1? Negative 2 times negative 1? Positive. Negative 1 squared is positive 1. 3 minus 1 is 2, which is positive and positive. So, concave up. And something less than negative 1.73. How about negative 5? Negative 2 times negative 5? 10. That's positive. Negative 5 squared is 25. 3 minus 25 is negative. So you got a positive times a negative, it's negative. It's concave down. So we can finally answer the question, which is asking where is it concave up and where is it concave down? It's concave up from negative root 3 to 0, non-inclusive, and also from root 3 to infinity. It's concave down from negative infinity to negative root 3, as well as from 0 to root 3. Non-inclusive for all that as well. And finally, we need to get our points of inflection. Well, every time the sign changes, you have one. So you're going to have one at negative root 3. You're going to have one because it goes from negative to plus. You're going to have one at 0 because it goes from plus to minus. And you're going to have one at root 3 because it goes from negative to plus. And now you have to plug all those into our original function. Oh gosh, look at that. Well, the 0 is not bad. If I put 0 in there, I get 0 over 0 plus 1 is 1. 0 over 1, 0. Good. So one of my inflection points is 0, 0. Now the other ones, the root 3 and the negative root 3, the bottom of both those things will be the same. If you square root 3, you get 3, and then you add 1, you get 4. So the denominator is going to be 4, and then the top's just going to be x, in this case, is root 3. So you're going to have root 3 over 4 in this one, and negative root 3 over 4 in this one. And at long last, we have done it. We have found all the information required, and we have finished this especially long video. Sorry, and take care.
Hold on, nothing's the same. Tell me why.